Galaxies can crash head-on at speeds of hundreds of thousands of meters per second. Yet their stars almost never collide because the average distance between stars is so vast that each star is like a grain of sand separated by kilometers. While gravity scrambles orbits and sculpts tidal tails, the luminous parts pass through mostly unscathed. Supermassive black holes at the centers spiral together over hundreds of millions of years, releasing gravitational waves. And the gas clouds, unlike the stars do, slam into each other, compressing into starburst nurseries that can form thousands of solar masses per year. And the final product is often a larger, calmer galaxy with a central bulge. Why colliding galaxies rarely shatter? The surprising physics behind cosmic crashes. Galactic collisions are common in the expanding universe because gravity binds galaxies in groups and clusters, but true destruction is rare. A galaxy is mostly empty space. If a star like the Sun were a 1-centimeter bead, the nearest star would be several hundred kilometers away. During an encounter, stars largely miss each other. Instead, gravity acts over long ranges, reshaping entire systems. Tidal forces pull out immense streams of stars and gas tidal tails, while dark matter halos interpenetrate and merge, deepening the shared gravitational well. This dynamical dance can take billions of years, marked by multiple close passes before final coalescence. Gas tells a different story. Unlike stars, interstellar gas clouds collide, shock, and lose orbital energy through radiation. These supersonic shocks compress gas to high densities, igniting intense episodes of star formation known as starbursts. Collisions can turn a few percent of available gas into stars within tens to hundreds of millions of years. Massive, short-lived stars then flood their surroundings with ultraviolet radiation and drive supernova feedback, which can either quench future star formation by heating or ejecting gas, or funnel gas toward the center to feed the central supermassive black hole. That inflow can trigger energetic active galactic nuclei, launching jets and winds that further regulate the new galaxy's growth. Computer simulations with millions to billions of particles reproduce these outcomes. Disks thicken, bars form, and orbital energy is converted into random motions. Two spiral galaxies of comparable mass often merge into an elliptical galaxy, with older, redder stellar populations and less cold gas. Minor mergers small galaxy into bigger, gentler, building up halos and faint shells. The Milky Way Galaxy is on a collision course with the Andromeda Galaxy. First contact in about 4 billion years will not pulverize either system, but will likely transform both into a single, larger galaxy over roughly another 2 billion years. The solar system may be tossed into a different orbital radius, yet the probability of the Sun striking another star remains extraordinarily small. Why do galaxies collide at all in a universe that is expanding? On large scales, space expands and separates distant structures, but within gravitationally bound regions, the local pull dominates over expansion. Dynamical friction gravitational drag from wakes induced in dark matter and stars bleeds orbital energy from the smaller galaxy, tightening the orbit until merger. Throughout, conservation laws rule. Total energy and momentum are conserved, while internal energy rises as ordered motions become random. Destruction would require efficient star-star collisions or wholesale disruption by tides exceeding self-gravity everywhere, conditions rarely met in realistic encounters. Observations across the electromagnetic spectrum validate this picture. Radio maps trace cold hydrogen gas inflows and shocks. Infrared images reveal dust-shrouded starbursts. Optical surveys show distorted bridges and tails. X-ray telescopes capture hot plasma heated by shocks and black hole activity. Gravitational wave observatories are closing in on the low-frequency signals expected from future supermassive black hole binaries. These multi-wavelength signatures, together with precise distance and velocity measurements in kilometers per second and sizes in kiloparsecs, show that galaxy mergers are engines of growth, transformation, and central black hole feeding, not cosmic demolition.